The following lesson covers frequency analysis, which is very important when talking about hydrology. Hydrology is very much statistically driven. What may happen last year may be different than what will happen today. Thus, understanding the probability of occurrence can be quite different from time and space. It is difficult as well, but this lesson should help clarify that. The learning objectives for this module are: where does the data come from? Before any kind of frequency analysis can be determined, we need data. Evaluating plotting position. How to determine the probability of occurrence of a specific event based on only that specific event and not any kind of frequency distribution. And then performing a frequency analysis, in this case a probability density function. So an introduction. Prior to running statistical analysis, we need data. So where does the data come from? It is important to realize the hydrologic design is centered around runoff, not the rainfall that generates runoff, and definitely not the watershed processes that transform rainfall into runoff. It's about the runoff. So we need to focus on runoff. In order to focus on runoff, we can visit the following website developed by the USGS. The USGS has many gauges located throughout the United States. Each state has specific gauges. By going to a state-specific gauge, you can determine what a hydrograph, or how flow with respect to time, will look like. So this is the Russian River in Ukiah, California, which is in Northern California. It shows you the runoff from April 11th through April 18th. As you can see, around the end of April 12th, and into April 13th, there was a high runoff event, suggesting that there must have been a rainfall event that caused runoff. These graphs that we're showing display flow as a function of time and space. So the Russian River near Ukiah, California is our space, and the time is on the x-axis. As I've mentioned multiple times, this is referred to as a hydrograph. Not a hydrograph, as we discussed in precipitation, but a hydrograph. Next, we're going to gauge the river. So, where do you place the gauge? What's really important when placing a gauge is you want to place a gauge in a hard point, like a bridge or a bedrock. Somewhere where the river does not move, a grade or degrade, erosion, or deposition, or even lateral migration. Imagine putting a bridge where the river will move. The cost of replacing that bridge or the damage it may cause will be catastrophic. Therefore, since we're going to put a gauge in a river, let's also put it in a place where it's hard. Next, we decide where to place the gauge in the river. We're gonna just look at that cross section as shown in the schematic. So we have a plan view and we have a cross-sectional view. So we're going to survey that cross-section. So we're going to use survey equipment to measure the cross-sectional area. We will measure that cross-sectional area at various depths so that we can calculate different areas. At each of those depths where the flow is occurring, we will measure the velocity. And then, by using the continuity equation, we will determine the flow rate as a function of area and velocity. Next, we'll create a rating curve. We will take all our measured depths and all our calculated flow rates from the continuity equation and sketch it. Put it into Excel and create a power regression equation such that the flow rate located on our y-axis, Q, and depth on our x-axis will plot, and then we can fit a best fit line through it. This power regression is represented as Q equals A times the depth raised to the b power, where a and b are constants based on a given location. Next, so that we can determine the flow rate at any given point, we put a gauging house on our river at that location and connect the gauging house to the river, as shown. When water isn't present in the river, it'll also be present in the pipe. We can stick a measurement tool that sends an electric signal to the house and gives us a depth measurement. Now we can measure the stage and calculate Q. So we measured the stage here, and we can convert it into an H. We can stick that H value into the rating equation and find the flow rate. Plotting position. Plotting position is yet another important concept. It's used from probability. So we go to the USGS website and obtain yearly peak runoff. Next, we rank the data from largest to smallest. So the highest runoff event will get the number 1, and the smallest runoff event will get the number n, where n represents the total number of data sets. We'll calculate the exceedance probability and the return period. The exceedance probability by definition is equal to the rank divided by n plus 1. While the time period is 1 over probability will give you the return period. This is usually in years, since our data was in years. If our data was in months, this time would be in months, and it would correspond. So let's do an example to make it clear. Imagine we have 4 years of data as shown, with the following flow rates. Let's first rank the flow rates based on the values. The highest getting a ranking of 1 and the lowest getting a ranking of 4. Next, let's calculate the probability. Remember, the probability is equal to the rank divided by n plus 1, in our case 4 plus 1, 5. Finally, the time period is the inverse of the exceedance probability. If you're having a hard time understanding exceedance probability, think of it this way. It's telling you that there's a 20% chance of getting a runoff event of 602 CFS or greater. There's a 40% chance of getting a runoff event that's 540 CFS or greater. There's an 80% chance of getting a runoff event of 382 CFS or greater. We'll do more examples of this to make it clear. Based on the position plotting, what is that 2-year rainfall runoff event? You'd have to interpolate, and you should get 486 CFS. Next is flood frequency. Now that we know where the data comes from and we can plot it on probability paper, we can now, because of Weibull position plotting, we now do frequency analysis. The first step is to identify the population. The population is usually identified based on using a histogram or a statistical test. For this class, I will always tell you the appropriate distribution. The first probability density function we will discuss is the normal distribution. It's the most frequent distribution and it's symmetrical. Over all values of x, the function looks as so. 1 over the standard deviation divided by the square root of 2 pi times the exponential of the quantity -1/2 times x minus x bar over s squared. Now, if we wanted to look at what this looks like, this is what the PDF looks like. We can integrate this function over from -infinity to infinity, and we can see what it looks like. The problem with integrating the f of x function of the normal distribution is it doesn't have a numerical solution. Therefore, normal tables were generated, where for every value of x, there's a corresponding z value. Z is equal to x minus x bar over s. The standard deviation for a normal table is 1. So this is our normal table. Inside of our normal tables are probability functions. Each probability function in this represents a non-exceedance probability. As you can see, the shaded region in the graph represents the cumulative distribution function. It represents the probability of something being less than. But in reality, when we're talking about hydrology, we're sometimes interested in more than. We want to know what's the likelihood of an event happening or greater than that event happening. So the way to read this is if you measured your z to be 1.00, your exceedance probability would be 0.84. If you measured your z to be negative 1.00, you would get 0.156. If you measured your z to be 1.65, you would get, right here, 0.95. So it's very key to using these tables, and it makes calculations much easier. We will utilize this in class to make this concept much clearer. The log normal on probability paper will appear concave. The distribution looks as such, and the only difference between the distribution is that you have to do a log transformation of the data. So all your x values need to be converted to y's. When you do that, the distribution will look normal. And you can then use the same procedure as the normal distribution. You then need to calculate the sample moments, the mean and the standard deviation for your data sets, so that you can plot it on probability paper. So if I use that example previously, we can plot our data on probability paper, where on the x-axis on the bottom is non-exceedance and above is exceedance. The y-axis is actually our flow rate. So the red dots represent those 4 points from previously, where I used the exceedance probability versus the flow rate to plot it. Next, I'm going to calculate the mean and the standard deviation of that data set, which I show. I then, for a standard deviation of 1, you have a non-exceedance probability of 84%, and for a negative 1, you have a non-exceedance probability of 16%. So I put x's at those two, and I make a linear distribution. This is my normal distribution. We'll talk about this more in detail in class to make this concept really clear. Should just be a quick review or an introduction with further clarification occurring during class.